to everyone to our first ITC lunch of the spring semester, and it does look like spring outside. I just wanted to start with two interesting developments. We heard first at the ITC colloquium today, we heard two very interesting talks from the Black Hole Initiative, one by Fabio Pacucci about the fact that perhaps some of the brightest quasars we see at high redshifts might be gravitationally lensed, and another one by Martin Lessourd that indicated that the interiors of black holes might be unstable if they are embedded in lambda CDM cosmology that we all love. So if you want more details for those that didn't come, speak with them. I wanted to start with the news that was on the front page of the New York Times this morning, a beautiful image of the sun. And actually a couple of years ago we went to Maui in Hawaii, and we were invited by the director of the Haleakala Observatory to visit this top of the mountain. That's my family. You can see yourself above the clouds, which is quite remarkable actually. It's on top of a mountain that is called after the sun, and it's very fitting that on top of this mountain NSF funded an observatory of the sun, and the first light from this observatory was released yesterday. And why don't you show the video, and I'll say a few words. Basically, what you see are the convective cells on the surface of the sun. And first stage, you might also see this.
Oh yeah, sorry.
And each of these cells is roughly the size of Texas, the state of Texas. But the resolution is such that we can resolve, over 100 kilometers the size of the island of Manhattan. And that's a fraction of an arc-second. Looking at the sun. Now, of course, in order for the telescope to operate, it needs a cooling system that is quite substantial. Most of the investment by NSF was for the cooling system, and they observe during the day. That's an unusual observatory. They look at the sun during the day. It's the only but the money was given to this observatory under the condition that they did not observe during the night, because the mountain is sacred to the local population. And in fact, the director told me that they paid a full-time job to a local priest, just to show you that they were much more accommodating to the local culture than the TMT was on the Little Mountain. And so as a result, this telescope was built, and it's getting the first light. The one thing that I found quite surprising is that the director was complaining that they don't get enough photons from the sun. Just to show you that astronomers complain no matter what. And the reason they don't have enough photons, they want to see all these cells the way they move, and they want to take a spectrum of each of them such that they see what kind of lines and so forth, and what is the Doppler shift. And so they just barely have enough photons to get the spectral resolution and the spatial angular resolution they have, and get enough photons there to get the information they need. But the telescope heats up very quickly by focusing sunlight, and so that's the main challenge. The second thing I wanted to mention is an interesting event that took place on Tuesday. So happens that a new student from the physics department came to me last week, and I think she's here actually. Betty, who is she? No. Anyway, she came and asked to work on a thesis, and I woke up on Tuesday morning. I thought I'll think about what subject she might work on, and started working out some details on gravitational waves from the early universe. And then, while I was doing my calculations, I heard the helicopters, going above my home, and it was early in the morning, and I said, what is going on? I mean, is there a military operation here, or some exercise? And it didn't stop for half an hour, and I decided to come to work early, and then I get a phone call from my wife, and she says, check the news. And turns out that there is a the chair of the Harvard chemistry department was taken by FBI agents from his office at Harvard, but his home is just 100 feet from ours. And so the noise that I was hearing, and I didn't look through the window, it sounded like an exercise, but it was actually a raid of the FBI agents on that home, taking out boxes of everything, cleaning up all the computers that were in the home. And it's a very unusual situation to yeah. That's the way I justify it. He is. Yeah. But actually, as we speak this morning, he is at the Boston court in Boston, and it will be interesting to see what the judge will say. Basically, he is being charged by the federal authorities for not disclosing connections to China on grants that he received from the NIH and from other. He got a lot of money. I mean, he is the most important person in nanotechnology application to biology in the world. And between 2000 and 2010 was selected to be as the most prominent person in that field. But apparently the rules changed over the past few years with respect to China, and he did not disclose his connections. And that's a very unusual circumstances, and Harvard actually formally did not. The president of Harvard did not say anything as of yet. I mean, it's just the legal counsel said something that they're taking it very seriously. Anyway, let's get into science.
I'll put one more note that's happening today. Somewhat sad note for some of us, but in a few hours, the Spitzer Space Telescope will be turned off. End of mission.
Well, we should voice Spitzer had a very glorious life, and we're all proud of the role that CFA And I should also mention with respect to the sun, since we talked about the sun before, there will be a CFA colloquium on the sun related to the Parker Solar Probe, and Justin Kasper, one of the lead scientists sitting somewhere here, he used to be at the CFA, will tell us a little more about it later at lunch. So we'll start with Rebecca Nevin from the CFA, and she will tell us about combining images in kinematics to identify galaxy mergers. Then we'll hear from Justin about the Parking Solar Probe. He's currently in Michigan, a professor at the University of Michigan. And then we'll hear from Martin Lessourd, again, a postdoc from the Black Hole Initiative here at Harvard. He will talk about the aspects of the mathematics of black holes. And finally, we'll conclude with Roger Blandford, who is visiting us for the week. Is Roger here, by the way? Yeah. Oh, he's very quiet. But we all look forward to hearing from him. He gave a talk yesterday, Steve Murray, and will tell us about fast radio bursts as Magnetar electromagnetic pulsators.
No.
Come on, go on. EMPs. Yeah, whatever it is. What is EMP, Roger?
EMP is an electromagnetic pulse that I could talk about that, but if you wanted, but I got prepared for something slightly different.
Oh, okay, but that's the title I got, sorry. Okay, so now we are even intrigued to wait and see what the test is. Okay, Rebecca.
Okay, we're live. Can you hear me? Okay, I can't tell if it's on. We'll say it's on. Okay, so if you take one thing away from this talk, I would love it to be that it's very, very hard to identify galaxy mergers. So my approach has been to combine the images and the kinematics of simulated galaxies to create a better identification scheme. So I'm showing you here, this is a major merger, which means that the two merging galaxies are roughly equal mass. And you might notice that the time bar is in gigayears. So one of the reasons that I'm using simulations is that I certainly am way too impatient to watch this happen in nature. So these are Mach images and Mach stellar velocity and Mach stellar velocity dispersion maps that I use in my technique to create a better merger identification scheme. Okay, so the motivation for looking at galaxy mergers comes from our very ideas about how the universe changes over time. So our idea is that smaller dark matter halos merge together to create larger dark matter halos, and this both contributes to the structures within galaxies themselves and the structures in the universe, like local clusters in the Illustris simulation, for example. Additionally, if you look at individual galaxies, such as this is one of my favorite galaxies, NGC 6240. Some people call it the turtle, some people call it the butterfly, kind of depends how you turn it. There's a lot going on here. This is a local major merger, so it's a really dramatic merger. And my group has studied both the star formation-driven outflow and the AGN-driven outflow in this galaxy. So from galaxies like this, it is apparent that mergers can be very, very important for driving evolutionary processes. However, if you look overall at the universe, the contribution of mergers to galaxy evolution is a little bit hazier. And this is for a couple of reasons. First of all, mergers come in a surprising diversity. So there aren't just major mergers, there are also minor mergers where the mass ratio is more unequal. There's also gas-poor mergers or gas-rich mergers. And identifying all of these different types of merging galaxies and understanding their contributions to galaxy evolution is really difficult. The second reason this is difficult is because we're all using different tools to do this. And so my analogy for this, and I really apologize if you've heard this analogy before, is actually apartment hunting in Boston. So some people are cringing already. I moved here, I had to live somewhere. I started looking for apartments online. You tend to get these beautiful luxury apartments in the ads when you're searching. These things are really shiny, beautiful, bright examples of apartments. They're kind of like the major mergers in the universe in Boston. However, I can't afford that, so I need to look at sites like Zillow. So this is a different search tool. It selects a different type of apartment. And even within this apartment tool, you might find apartments like this. This is a $1,000 per month apartment. It's one bedroom, and it's 4,000 square feet in Cambridge. I say, no way is that a real apartment. This is a false positive. This cannot be real. So even within these tools, you might get these false positives. So it's really important to understand what are the limitations and biases of the various tools you're using to do this job. However, I just needed to find one apartment. Yeah, don't look at the rest of this. I just needed one apartment. But what I want to do with mergers is actually select a wider diversity of mergers. So I'm still working on the merger side of this, but I finished with the apartment side of this. So my merger identification tool is novel because it uses both imaging and kinematics to identify galaxy mergers. And these are also standalone techniques. So I've created these to work individually, and I'll talk about them both individually, but it's really strong when you put both together. Okay, so first the imaging side of this approach. I mentioned I'm using simulations to train this approach. I'm using Gadget 3 sunrise simulations. So these are really high temporal, high spatial resolution simulations of two galaxies merging. So these are confusingly called isolated galaxy merger simulations. Okay, so you can also look at these galaxy mergers from many, many different viewpoints, and I have a couple different merger initial conditions. So I have some major mergers like you're seeing here, and I have some minor mergers, and I have some gas-rich, and I have some gas-poor mergers. Okay, also to mention here, I have some isolated galaxy mergers. So these are sort of like the control sample that I'm going to compare to my merging galaxies. I have a matched sample of isolated mergers, and I additionally take the galaxies from the very, very end after the merger has happened and call these isolated. So what I do is I take these beautiful simulations and I do this to them. I create mock images that match Sloan Digital Sky Survey imaging specifications. So I've labeled some of these with the various stages of the merger just to highlight that I'm covering the entire duration of the merger. And then what I'm doing with these images is I go out and I measure various things about them. And I call these imaging predictors. So just tools that are somewhat historic that do a good job of predicting if something is merging or not. And I've listed some of them here. This is asymmetry. You just flip the image, subtract it, and then look at the residual of that. Okay, so I measure all these different imaging predictors from these simulated galaxies. And I began by kind of looking at how do these imaging predictors, such as Gini, separate the populations of non-merging from merging galaxies. And I don't think they do a particularly good job individually. There's a lot of overlap here. So what I do is I combine all of these 6 imaging predictors into a 6-dimensional space, and I solve for the hyperplane in this space that best separates the population of non-merging from merging galaxies. So that hyperplane is called linear discriminant analysis. That hyperplane is called LD1. It's a really cool technique. And with LD1, I'm better able to separate the populations of merging from non-merging galaxies. This top plot is the major mergers. This bottom plot is the minor mergers. So this is more accurate and precise than any of the individual imaging predictors. Additionally, what's so interesting about this technique is that it's not a black box. You can actually look at what's happening, what individual imaging predictors are most responsible for this axis. So for the major mergers, asymmetry and shape asymmetry are really important, for example. And then you can do a lot of other things, like I've done some work analyzing, well, why is this technique so much better than the individual imaging predictors? And it turns out these individual predictors are picking out different stages and different types of mergers. And by combining them all together, you're really able to capture the full duration of these mergers. Okay, on to kinematics, since I only have 10 minutes. So I wouldn't be looking at stellar kinematics of galaxies if I didn't think they would be complementary to the imaging approach. So the clue for this is in other simulations that have been run. This is another galaxy merger simulation. KASIM is just a predictor that predicts how disordered is your kinematic map. And this predictor stays elevated for long after the merger has happened. So that was really interesting to me. Additionally, I'm motivated to create these mock stellar kinematic maps because of the MANGA survey. This is Sloan 4's IFU survey of galaxies. There are more than 10,000 galaxies in this survey. And so I thought, this is an amazing statistical sample. I would like to go ahead and sample these galaxies and create various subsamples of different types of mergers. So here are my mock kinematic maps that I've created to match the specifications of the MANGA survey. What I do is I extract various kinematic predictors from them, things like how similar is this to a rotating disk? I do some modeling. This is all also based on other historic predictors. And I construct this LD1 axis for these kinematic predictors. And if you remember what the previous plot looked like, this is a little bit different. It does a pretty good job of separating these populations, but you might notice there's a lot of overlap here, which I'm highlighting here. So this is from the imaging technique, which has less overlap. And I think the differences between these are really informative. So here, if we actually examine what are these galaxies that are false negatives, so these would be things you're missing. These are actually galaxies that are in the process of merging. They look like they're merging and imaging, but the disk remains ordered, so the stars aren't that disturbed. Whereas these things, these are the false positives. Those are like that weird apartment that can't too good to be true. These are things, I'm in the way, that are late in the merger, well after it has merged, that remain, there's a tiny little kinematic warp in this map. So these features actually remain in the disks. Okay, so my goal with both of these tools is to actually go ahead and apply them to both Sloan imaging and MANGA, which I'm in the process of doing and creating various subsamples of merging galaxies. And with those subsamples, I'll of course answer questions about what are the various evolutionary processes happening in these subsamples of galaxies. But the future goals, beyond just applying it to what I immediately prepared it for, are also to apply it to other surveys. So I want this tool to be adaptive to HST, JWST, LSST, not just imaging, but also IFU. And this summer, I'm really excited because a student from University of Colorado, Amy Schechter, will be here. And she and I are working on pushing this to higher redshifts. So right now, my technique is just for the local universe. With her, the goal is really to extend this and look at different redshifts of mergers. Okay, I'll just leave this here. Thank you. Oh, yeah, I was like, SCSS? No. Okay.
Obviously for mergers, the outer part of the merger needs more time to actually, the time depends longer. So you have more chance of seeing that symmetry is there, but there is a surface brightness.
Right,
So it
yeah.
depends on how high redshift.
Yeah, all this is also so dependent on what are the specifications of the survey. So, of course, I've only looked at Sloan imaging. I've looked a little bit at HST, and I think it's a totally different ballgame when you start to be able to see a little bit deeper with these images. Yeah.
So this is very nice because you're putting these two different types of features together. What about things like color, for example, or star formation rate? Are these things that you're also considering adding, or do you think that it might not substantially change what you're already getting?
Yes, so that's a great question. I have thought about color. So, for example, you could look at different filters. And the great thing about these simulations is that they pop out in the radiative transfer. They have a bunch of different filters you could play with. So one question that you could ask is, which filter is most predictive for various different types of mergers? And that's a future project. I'm definitely heading in that direction, maybe with another student. In terms of star formation rate, that's something we're trying to look at once we've identified the populations, because that's a key science question for why do we need mergers at all. Yeah.
Thank you.
Yeah. Yeah.
Obviously, all galaxies, given the hierarchical model, are going through mergers at some point or another and have been through a merger. How do you precisely define a non-merging galaxy? How far after a merger is it become a non-merging galaxy?
Right. So currently, I say 0.5 gigayears after your nuclei coalesce, you are no longer merging. So everyone kind of has to decide, what is the cutoff? And it turns out that cutoff works a lot better for the images. They really don't look like they're merging in the Sloan imaging after that time frame. But then I'm running into this problem where the stellar kinematics look like they're still merging after that point.
Is there a physical basis to judge this by? Is there a...
Yeah. Yeah, so the question is, physically, why would you choose that cutoff, right? This is all in my paper, and I'm forgetting exactly why I did. But it was based on past work. I think everyone kind of has to decide at which point do they stop merging. And, of course, the other limitation is that these are just isolated galaxy mergers. So we're just merging two, and that's it. It's over. Whereas in reality, this is a much more cosmological thing. So the important thing is to also look at cosmological simulations, because more than two things can merge and things can come in and disrupt the merger.
Okay,
Yeah.
Then if a high redshift, half a gigayear becomes quite a bit longer than half a gigayear today.
Right. So as we push to higher redshift, we're thinking about looking more at the cosmological simulations as opposed to just the isolated ones. Okay, thank you.
Thank you for this chance to share some supplemental information about Parker Solar Probe. At the CFA colloquium today, I'm going to talk about the reason we're doing the mission, the CFA's role in its success, and some of our initial science discoveries. What I want to do here today is give you some examples of why I think you might care about the results. I'm not trying to be defensive here. We have 50 papers coming out in AppJ in February, and there's a lot of material in there. And I think some of the discoveries are going to be really useful for astrophysics in general. So I want to bring your attention to some of the things I wouldn't normally highlight in a random talk on this. So one of the things I want to talk about here is what we're seeing in terms of the heat flux and the non-thermal nature of the solar wind, both ions and electrons. What do I mean by non-thermal? The distribution function in velocity space no longer looks Maxwellian. Now that could be, there are two Maxwellians, it splits in half. It has all sorts of weird shapes we have no analytic explanation or form for. I'll show you examples of this here. Now, why should you care? I think most of the time this feels like a detail, right? Like, I don't care how the heat flux is actually transported through my fluid. You know, there's a temperature gradient and the heat's flowing, and that's it. Well, we have examples where we really wish we knew the exact pitch angle and energy distribution of non-thermal electrons. For instance, I'm just picking a random example here that's a little timely. We have these beautiful simulations of what emission might look like from a black hole. This is a simulation to compare with the Event Horizon Telescope results. And unfortunately, I think if you'll ask anyone doing these simulations to be honest and confess, they're making up a model or an approximation for the electron pitch angle distribution. If I change that model, I can get whatever emission pattern I want out of this. And so until we have another constraint on what the energy and pitch angle distribution of electrons near accreting on the black holes is like, we don't really know what to plug into these simulations. So my goal here is not to say give up, plasma is hard. I want to show you some cool things we're starting to find with the Parker Solar Probe that'll maybe help us answer some of these questions. This is the most texty slide I have. Just a little reminder, what actually determines heat flux? Heat flux is related to temperature gradients. You know, if one region's hotter, heat should be flowing from the hotter region to the cooler region. How do you transport heat? You know, in a gas in this room, it's pretty straightforward. There's so many collisions. Everything's Maxwellian, and any temperature gradient in some local location is associated with the heat flux, determined pretty much solely by a little bit of physics and the temperature gradient. And that's it. You don't care about what the rest of the air in the room is doing. And what happens when you move to a collisionless plasma, like the solar corona or solar wind, a supernova shock, the ISM, a black hole accretion disk, or at least parts of it? Now the problem is the heat flux becomes non-local. So if the mean free path for collisions between individual particles becomes a lot larger than the gradient scale of the electrons, now you have a very complicated mechanism for the heat flux to be transported. The distribution function is no longer going to be able to be approximated by just a drifting Maxwellian. So how do you actually treat it? What are the closed forms for heat flux? There are none, or not analytically solved. What we do is we just truncate our descriptions of velocity distribution functions when we go to fluid and moment equations. So for instance, what are some famous approximations for heat flux? The free streaming heat flux is a pretty common example. How much heat could electrons possibly be carrying? Well, an extreme is to say, what if I take the entire kinetic energy of the electrons and I have it flow at the thermal speed of the electrons, basically flowing at the sound speed? That's got to be an upper limit for how much they could carry. An example in a collisionless plasma of an attempt to quantify the overall heat flux in units of this free streaming flux is this Spitzer-Harm relation here, which has also some physics, gradients of electron temperature. And it turns out in the solar wind, if you make a ton of approximations and scalings, you get that the fraction of the heat flux relative to this free streaming limit should scale as something like the mean free path of particles versus the length scale of temperature gradients. And a recent, well, I say recent, this is now from 2013, a recent result that was published using data at 1 astronomical unit that I think you might all find interesting is a plot using decades of data in the solar wind at 1 AU, measuring the heat flux, comparing the heat flux to the free streaming limit, and plotting it versus this mean free path versus the length scale. And what you can see is when the plasma is collisionless, when the mean free path rises above a few times the temperature gradient scale, then the heat flux locks in at a constant fraction of this free streaming limit. It's not actually the free streaming limit. For solar wind plasma, it turns out to be about a third of it, but that's really useful to know, right? How universal is that? I don't know. One of the nice things about Solar Probe is we're going to a very different region, different plasma beta, different temperatures, collision scales, gyro frequencies. So we get to now see how universal something like this is. And then below this region, as the plasma starts to become more collisional, we see this Spitzer-Harm relationship. So what are we seeing with Parker Solar Probe? I'm going to say just 2 slides about what distribution functions look like in space as a refresher, and then we'll dive into just some random examples of odd things we're seeing with probe. So first of all, the 0th order, what do the velocity distribution functions of ions and electrons look like in the solar wind? From the point of view of a spacecraft essentially motionless with respect to the sun. You see protons and alpha particles, hydrogen and helium, that's the bulk of the ions in the solar wind. They're supersonic, so they're moving away from the sun at, by the time you're at 1 AU, 10 or 20 times the speed of sound. And they have very thin thermal widths, but they look Maxwellian. The electrons have about the same temperature, although it can vary. They can be 10 times hotter, they can be 10 times cooler. That's something else we have yet to explain, why you have that big a discrepancy. But the electrons are subsonic. And so it's a very interesting situation. You see electrons coming from every direction of the solar wind. That is not what the electron velocity distribution function actually looks like at 1 AU, or in space. So one of the reasons I love studying space plasmas is I get to do something I don't think you can do anywhere else. You can't do it in a lab, you can't do it well in a simulation yet, you can't do it with a telescope, and that's actually measure the number of particles as a function of velocity at one point in space. And so what do we find? Typically, the electron velocity distribution function in space is not a Maxwellian. It has a Maxwellian core, which I show with this blue line, right? So just a simple single temperature, nicely, bell curve shape. That makes sense. But then, in every direction, it has what we've decided to call a halo, which, if you're interested in the details, seems to be well described by what we call a kappa distribution. So not quite a power law tails, but there's a non-thermal bend, and then there's an extension in all directions up to higher energy. That's the halo. So this is one superthermal or non-thermal component of the electrons in space. And then we have this other wild thing we call the strahl, which if you're an optical astronomer, you think we stole your term. I don't know what to say. But the strahl is a beam of electrons traveling along the magnetic field. And so this is the heat flux. All right? Now, actually, it can get a little more complicated. The core and the halo don't have to be moving at the same speed. So they can actually carry a little heat flux between them. But most of the heat flux is carried by this thing here. And we wish we had an analytic expression for this and understood what makes it and how it goes away. Okay, so now that you know what some of the curious things we're trying to understand, I'm just going to give you a potpourri of bizarre results I hope you'll hear about more as time goes on. So these are some plots of raw data just to show you what a velocity distribution function looks like. These are measurements of protons and alpha particles measured by the Solar Probe Cup, built at SAO, prepared by Mike Stevens and Tony Case. And so we're looking very close to Parker Solar Probe's first perihelion encounter with the sun at 35 solar radii. And what you can see, let me start with this one. Hydrogen peak, nice Maxwellian distribution, I can fit it. A weird little bump here that's also hydrogen, but kind of asymmetric. And then this is actually doubly ionized helium. It should be a 2. Okay, that's a little strange. How about this one? Here's a proton Maxwellian distribution function. Here's another proton Maxwellian distribution function. They're flowing through each other at about 200 kilometers per second, nearly the speed of the wind itself. That's possible because it's slightly less than local Alfvén speed, and for some reason, which we don't understand, you can have insanely large differential flows as long as they're less than the local Alfvén speed. We think an instability limits it. What's creating these beams? Why are they so big? Why are they moving so fast? We don't know. But they become very large as we got close to the sun. Here's an example where they're nearly equal density. So, this is no longer some sample tracer population that's along for the ride. It's half of the mass flux of the solar wind is moving at the wrong speed. And by the way, everyone wants, a lot of people don't care about this, right? They want us to publish the density, the speed, and the temperature of the solar wind. Well, what am I supposed to tell them is the temperature of the protons in the solar wind here? If I include the energy in that differential flow, some of these turn out to be 50 megakelvin plasmas. Maybe that's the case. I mean, that's how much internal energy they're carrying. Okay, now let's quantify this another way. Here is a velocity distribution function measured pretty far from the sun in the solid, and the dashed line is the best fit of a Maxwellian. Fits pretty well. Here, unfortunately, is a pretty typical example of a velocity distribution function of the protons close to the sun, and it's spread out. And what we have here, which I won't go into, is there is almost all the time as we get close to the sun, protons don't look Maxwellian anymore. They're flat-topped, they have a huge skew, they're not Maxwellian. This is not like a freak event where things were knocked out of equilibrium. That is the dynamic equilibrium state of the solar wind. And we are only at 35 solar radii. Yesterday we passed 28 solar radii from the sun. At the end of the mission, we'll be at 10 solar radii. So just how much stranger is this all going to get? And I just want to show you one more teaser. Lots of waves, fascinating. This was the first encounter with the sun. If you want to know what all the plots are, come to my talk this afternoon. This, and this is 11 days total, this is the radial component of the magnetic field. All right, we spent the entire time passing through a region of the sun with magnetic field that pointed back inwards towards the sun. Okay? Do you see all these times it crosses over to the other polarity? That's not supposed to happen. Every model of turbulence in the Cronin solar wind begins with delta B over B is much less than 1. So one of our big shocks with the fields that we're finding is this plasma has a huge amplitude of fluctuations, which we were not expecting. And that's going to, unfortunately, well, or fortunately, make us, I think, rewrite how we think transport dissipation is happening in the corona. So that's just a little potpourri, I'm done there, of some of the aspects of what we're finding with probe that I think you're going to find really interesting over time. Okay, and maybe we have a little time for questions. Oh yeah, definitely. So for the electrons, that kappa, at some point, if you're willing to go up high enough, the kappa looks a lot like often looks a lot like just a power law distribution. And then for the ions, we're not quite there yet to be able to make that measurement, but we will be. And that's something we're very interested in. And we go all the way up to hundreds of keV and MeV between the different instrument suites. So we're very interested in that. With the electrons, I won't even show you because it's a lot of plots, but we're finding really intense coherent fluctuations near the electron cyclotron frequency most of the time in the wind, really strong Langmuir waves associated with some properties of the differential flow and how large the heat flux is. So we think we're finding evidence that it really is wave-particle interactions are limiting the heat flux and accelerating the particles, but which is coming first, we're not sure. The alphas rarely have beams, but they can look non-Maxwellian also. One of the fun things we like to study is if the collision rate is low in the solar wind, the alphas can be 4 to 8 times hotter than the protons. Now, if you thought for some reason there was a wave-particle process that was giving them equal thermal speeds, you might expect a temperature ratio of 4. 8's kind of supercharged heating, and like iron can get up to 100 times hotter than the protons in the solar wind. The main departure from Maxwellian, so they're Maxwellian but different temperatures. The main departure from a simple Maxwellian is they can have huge temperature anisotropies. So, a lot of this plasma as we got close to the sun, not a lot of it, but some of the plasma as we got close to the sun, we started seeing the temperature perpendicular to the magnetic field was 8 to 10 times the temperature parallel to the magnetic field. So that's a huge difference in pressures.
Very quickly, yeah. You have this lambda mean free path.
Yes.
Is that the Coulomb?
It's the Coulomb, yeah.
Not the Larmor radius.
Exactly, it's the Coulomb, yeah.
It's the Coulomb.
Yeah. So, and just so you know, for a typical ion or electron, once it leaves the lower corona, that mean free path is around 1 AU. So, quite long. Yeah. Oh yeah, definitely. For the ions, I don't know. The ions really seem to have a rich number of kinetic instabilities that prevent them from developing like too extreme a tail. Okay. Thanks. We broke the sun. Oh, I can't believe those people. Oh, wait, no, my mic's still on.
So hi everyone. So the usual in mathematics is that we give talks on the board. I know this is an astrophysics department, so I apologize if it's not in line with what's usually done. I will be talking today about two methods that have been kind of understood, discovered to make a black hole. So that's the challenge. So there are two methods, broadly speaking. I'll describe them in a little detail. I won't go through anything like the real statements or the proofs, of course, but I'll go through these two methods, roughly what they say, and then in the last 2-3 minutes, I'll talk about some recent work joint with Professor Yao, where we've been able to, in a sense, give the first statement in the direction of what's called the Hoop conjecture. To some of those around you may know what the Hoop conjecture is. It was Kip Thorne's 1972 deliberately vaguely formulated plea to the geometers to try and find a statement of the kind: if the matter energy associated with some S2 is sufficiently large compared to perhaps some boundary geometry, say the radius or something of this kind, then there must be a black hole inside. Loosely speaking, if you shove enough stuff in a small enough region, there will be a black hole. So that's the Hoop conjecture. So I'll talk about three things. How to make a black hole as it was understood in 1983, discovered by Shane Yao. How to make a black hole discovered by Christodoulou in 2008, which is a totally different kind of making of a black hole procedure. And finally, I'll just mention this brief result that we have. So everything, of course, takes place in a Lorentzian manifold, n+1, that satisfies the Einstein equation. It can be the vacuum case, or we can add some matter, that's fine. And for any initial data set that fits inside this manifold, I can consider some hypersurface. I'm going to label this with mgk, and this is my initial data set that has to satisfy the constraints, which are the equations that the scalar curvature of the initial data set related to the second fundamental form is given by the time-like contraction of the stress-energy tensor, where in the case with energy, I add in my usual Einstein tensor term. This is a scalar curvature of G equals 8 pi T stress-energy tensor. So this is an initial data set. It's a Cauchy slice. It's a time slice. It's what you start with, and you either evolve it, you look at it, you study it. The second part of the Einstein equation is the divergence equation for the second fundamental form. And basically, this is, in a sense, the angular momentum, the local angular momentum associated with the initial data set. So there's two groups in mathematical general relativity. They're the groups that stay static in their chairs, just as yourself, or they're the group that evolve. They solve the Cauchy problem, and they try to prove that things go a certain way if we turn the clock on. So these equations are a mixed elliptic hyperbolic system of equations, and this is just the elliptic part of the equations, namely what happens on the data set. All right, necessary and sufficient condition for this to embed isometrically into a Lorentzian manifold. Right? So the two makings of a black hole, the two methods we know how to make a black hole, come from Shane Yao in 1983, using their work on the positive mass theorem. And later I'll talk about Christodoulou in 2008. And this is the evolutionary part. So Shane Yao, what do? Essentially, they take a data set, okay, and they make this data set satisfy the constraint equations. So it's a necessary and sufficient condition for solving this Einstein equation. Then they consider some bounded domain, and then they're going to start cranking up the geometry by cranking up mu, which is the stress energy tensor contracted with the time-like normal of this initial data set. Now you crank it, you crank it, you crank it, you get bigger, 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 and then finally you get the beginnings of a black hole, namely what's called a minimal surface. That's the surface where, on my diagram, as you see, the the interior of the domain is curving in on itself. That's that hypersurface there in the domain is what's called a minimal surface. The mean curvature is 0, and that's what we say in mathematical relativity. That's what we know corresponds to a black hole when we consider this initial data set. So that's how they did it. They cranked up the geometry. The actual process of how you do this mathematically is not something that we can go into in the time given. But it was a very beautiful proof, very non-trivial. I mean, all kinds of techniques from geometric analysis, PDE theory, etc., etc. But this is the rough picture. Now, I'm going to talk to you about a different proof, the Christodoulou 2008. And hopefully, I just want to convey the basic idea here is that there are two ways to make a black hole. One is to send lots of energy towards one another, lots of gravitational waves towards one another, like a focusing beam. And the other is just to crank up the amount of stress energy in some given region. Okay? So how does the other one work? Well, the other one has T equals 0, so it's a purely vacuum solution. And one starts with, say, a big sphere, like this. And on this sphere, I can consider little coordinate patches, right? So these are, I'm drawing these, but imagine that they really cover the full sphere. I'm only going to draw a couple. I don't want to spend too much time drawing too many. But basically, you ought to think of this sphere as just sitting out there in space. And then what you're going to do is you're going to send in gravitational radiation, right? Now, the mathematical term for this is the shear part of the null second fundamental form associated with the double null foliation, et cetera, et cetera, et cetera, blah, blah, blah. We're not going to go through that, but basically you send in radiation along all these patches, all these coordinate patches on the sphere. Now, then, this was your initial sphere. What are you going to do? You're going to shine a light cone. So now, you have a light cone. Okay. So light cone is just, if you like, spanned by all the outgoing null geodesics sent from this sphere. And what you're going to do is that for each level set, each instant in time, if you will, of this outward goings light cone, you're going to consider a sphere which foliates this outgoing light cone. So in this, I actually had space to draw the sphere. In this one, I'm only drawing a circle because I'm collapsing the other directions because I don't want the diagram to get too messy. But essentially, each one of these level sets, each one of these guys, I can have another one here. I'm not going to draw it because it's going to get too messy. But each one of these guys actually corresponds exactly to one of these spheres. And so what you're doing is you're sending in radiations, radiation, all the way, each along the way of the light cone. Then you consider, this is when the diagram is going to get messy. So for those at the back, I'm sorry. Then you consider, actually, let me extend this diagram. This diagram is clear enough, right? Let's get rid of it. So this is Christodoulou. (2008). So take this sphere, but now I'm going to collapse again the dimensions. So I'm not going to draw the whole sphere, but I'm still going to draw the outgoing light cone. Let's draw it big. And now I'm going to draw an ingoing light cone. Like this, and like this. So now, I can draw, once again, the outgoing light cone from the edge of the ingoing light cone. And likewise, I can draw an ingoing light cone from the edge of the outgoing light cone. Okay? And what you're seeing, this circle here is this sphere. Okay? And every single one of these circles is, again, this sphere. So what am I doing? I'm sending in radiation along here. Radiation, radiation, radiation. And basically, the rest of the story is a 600-page manuscript in hyperbolic PDE. And what do I show you? I show you that this circle up here at the top of the diagram, or chosen parameters, has the property that it is trapped. what is a trapped surface? It's a surface such that if I send light cones going outwards, then if I consider null geodesics, which are going outside, these guys get focused in by the strength of the gravitational field. And when we think of a black hole, that's exactly what we think of. We think of a black hole as being an interior and an exterior, and everything in the interior is trapped. So this is the second way of making a black hole. You focus in gravitational waves, you shoot laser beams. So if all of us in the room did this, and we pointed it all towards one point in the middle, and we all actually had laser guns, say, then we would all focus in our laser guns, and there would be a bright spot just about here where everybody is doing this, and then this spot would be kind of high intensity. But the same is happening here with gravity. So the waves, the gravity waves, are being focused in, and they're focusing in onto this final sphere that's so focused, it's trapped. Okay, so that's Christodoulou. The Shenyao proof is about, in total, 100 pages, but the Christodoulou proof is much harder, 600 pages, because you have to evolve the whole space-time. It's not done on an initial data set, it's done in the evolution. Right, so now, just for 2 minutes, or 1 minute at the end, let me just describe what we did with Yao. I'm just very, very quickly. How many pages? Well, it relies on a lot of theory. So what we did was just kind of improve the Shenyao argument from 1983. So what did we do? Well, we took as you know, in general relativity, when you take an initial data set, there's no well-defined notion of mass. But when the thing's asymptotically flat, then you can define something called the ADM mass, which comes from some other thing that we don't have time to go into. But the point is that you can think of a quasi-local quantity. This is now an S2 with an induced metric G, nothing to do with this G. But of course, this is embedded in an initial data set, right? And this initial data set is going to satisfy the constraints. That's going to be where your PDE is going to be doing the work for you. And the idea is to come up with a quantity that's some integral of some blah, blah, blah. Nobody knows really what the best definition is, but you come up with the best definition you can. Basically, by the way, between you and me, that's just the definition for which you can prove a theorem. But anyway, a physicist would hate this. A physicist would say, no, come up with the right definition. But mathematicians say, well, no, look, I just want to prove a theorem, okay? That's all I want to do. But anyway, you come up with this quasi-local mass quantity. And then what you do is you say that if the quasi-local mass is bigger than, say, the diameter of the boundary, right? This is omega. This has boundary partial omega. And if you define your mass sufficiently well, so these question marks take basically an hour to define, by the way. So let's not go into that. But anyway, you can prove a theorem of this kind, that if this is true, then there is a black hole inside. In other words, the interior looks like this, and there's a minimal surface here. So that is the first time anyone has proven a statement of this kind, a statement namely in the Hooke conjecture. Kip Thorne tried to conjecture something like this, and this is the first time people have actually proved a statement of this form. Anyway, thank you for listening.
In astrophysics, we just naked. But the talk that you just heard, is an example of the kind of science done at the Black Hole Initiative. We have an exceptional group of postdocs over there. Any questions to Martin?
Is it fair to characterize you've taken an important step along the road to proving the Hooke conjecture, but haven't proven it yet? Is that right?
So I would now we're getting into politics. Good. So I would say the following. I would say the Hooke conjecture was never really a conjecture. It was a plea to mathematicians to come up with a statement of the kind that Thorne had in mind. But when Thorne stated it, he neither gave a definition of mass, neither gave a definition of the boundary geometry quantity that he wanted anyone to prove this statement with. So in other words, it was just prove a statement of this kind. And so what we did was find definitions for which we can realize Thorne's conjecture. So that's my sliding away from your question.
Any other questions? Yes, go ahead.
So it gave this example with all of us standing with laser guns and pointing to. So actually, this will also make a black hole, right? But this is more like the first. But this with the laser guns instead of the gravitational waves. But this would be more of the first kind because that's you're like making a curvature in the space.
Right, okay, so okay, yeah, that's right, but the laser gun I had in mind when I was saying that was a laser gun of gravitational waves.
I have this at home.
Yeah. Maybe we can have fun with it later in the garden. We can. All right, thank you very much.
Let's thank Martin again.
Okay, looks like it's working. Okay, good. Okay, so I'm sorry this is not the advertised talk, but there seemed to be some confusion. It was almost certainly my fault, but there were a few things I said could talk about, and this was the one that I eventually chose. And it's something that is actually high energy astrophysics in the sense it's related to cosmic rays, as you'll see. But the problem is biological. To explain the sort of handedness of biological molecules and life, and the genesis of this work, excuse the expression, is my colleague Naomi Globus came up with all the central ideas here, and due to her, and she bullied me into working on this, and I'm very glad that I did, because it's been exciting and very interesting. I think the ideas, the key ones are original, but I'm sort of, we're obviously learning a lot, and we've got two physicists blundering around in a large, complicated field that they know very little about. So what could possibly go wrong with that? So at any rate, I just wanted to emphasise that the central ideas are hers, and I think they're very interesting. Okay, so where are we? Okay, so the basic idea is to try and understand the handedness of biological molecules, and I think everyone's aware that there is this. Forget the words left and right, because they're terribly confusing in this context, as they mean different things as always. But there are two systems, and we'll call one of them live and the other one evil. This is the good stuff, is the live here, and they all fit together, and you can imagine a mirror universe in which all the same processes, including Abby introducing this talk, can happen in a completely mirror symmetric way. And our contention is, and we'll argue this, obviously not originally, that the choice that has actually been made, at least by most of us in this room, is essentially a causal one. And if you think about it, the causality really goes back to the atomic physics of carbon and so on. That's really what induces this. Okay, so this is the sort of, if you like, the cartoon here of living systems, and the whole one system that's chosen is essentially a causal process. Why you chose that, and obviously that's a highly testable proposition. Okay, so how do we suggest that this might have happened? And here we invoke cosmic rays. And obviously, we're thinking very much here about the very early very early solar system, and the very earliest life forms. And we're not talking about people with antennae on their head saying, "Take me to your leader." We're talking about something very, very primitive, probably more primitive even than RNA, and certainly not DNA, which is a very well-oiled replicating biological system. RNA can replicate, but in a very clumsy and rather inefficient way, and we're probably talking about something even more primitive than that, which is going to become RNA in the course of time, but it's struggling to replicate and struggling to mutate and struggling to explore all sorts of possibilities. Whimsically, I've called this sort of moxie nucleic acid, in the sense that you admire its spirit in doing this, but it's not serious. But this is sort of the territory if we're in, if you like. And now the cosmic rays themselves, sorry, something sit there. Basically, the point about those is, if you're a physicist, you start saying, well, what's making chirality? And you start thinking about the weak interaction immediately. And the one place where this is expressed is in cosmic rays, because of the neutrino itself. It's not the neutrino that matters, it's the muons that are made in the atmosphere, which then make, made by pions that make the muons, and the muons then make electrons and positrons, and they obviously have spin, and after, in kinematics, that's expressed in the cosmic rays, and the bottom line is that both signs of muons and electrons, charge for muons and electrons, have magnetic moments that are anti-parallel to their velocity, if you think about it. So it's not helicity, it's the magnetic moment projected on the direction of motion that matters. So we call this lodacity after Lodestone and so on. And the key thing is that this is, when you make the muons, this is the word, it's essentially totally total, if you like, and then that degrades as showers develop and so on, and as particles lose their energy propagating through the atmosphere. So I think we sort of understand this. It's actually quite complicated. We've discovered things that should be in shower models and so on, in particular Mott scattering, when you get symmetry effects with identical particle scattering and so on, but those are small details. The basic point is that cosmic rays are physically chiral because of the weak interaction as they irradiate stuff on the surface of the Earth. But what you actually have, it depends very much on the environment. We call this a fount, and there are many, many possibilities here. It could be a puddle on the surface of the Earth. It could be something out in an asteroid in interstellar space. Most likely, I personally think, anything that is going to be prosecuted, in fact, all throughout the universe, life and so on, is going to be underground, because cosmic rays are extremely damaging. You wouldn't want to live on the surface of Mars, and I'm not quite sure anybody imagines they're going to do that. So I think, driving to the supermarket and so on, 200 meters underground is far more likely than having, we're in a really rather privileged condition, and the early Earth was, the sun was going to be much more active in the past and so on. So this is the basic idea, is that you have this elasticity, and so you've then got this sort of picture. Now, how is this actually expressed in an interaction? And again, as we don't know the molecules we're talking about, it's even a bigger jump to say, how does this get translated into a replication mutation and so on. But just imagine, just as a thought experiment, to sort of start thinking the right way, let's have some site here where we might be trying to ionize an electron from a very simple chiral unit. And the simplest chiral unit is something like that. I'll show you my right hand, I suppose I should. Come with me. Okay, and so you've got something down there, and you want to ionize from there, and then you've got 3 bonds. And it matters that, not that there are different charges on them, but they're of different lengths. Otherwise, for these purposes, it's not essentially chiral. So, and this is the sort of molecular version of it, if you like. And so, the way this actually works is it's easiest to think about this classically. Just have a cosmic ray coming in. You've got to involve all 3 of these bonds to get to that point. And so there's a first order perturbation, which might be, say, that one there, which is going to deflect the cosmic ray due to its electric field. It's an electric calculation. This one here, there's going to be the sort of spin orbit type term that you're all familiar with. The V cross E is going to look like a magnetic field. And so that then gives you a coupling to the induced magnetic field due to the Lorentz transformation. And then the third one, in the sort of simplest expression of this, might be this gives you a displacement down here, but then the electric field due to this third bond here then gives you a change in the energy of the particle at that space. And so this is just, if you like, a simple chiral unit, and it shows how you will get a preference, a tiny preference for one helicity over the other when coupled to a cosmic ray with magnetic moment along the antiparallel to the velocity. So this is a very tiny chiral preference, and it's basically sort of third order perturbations, because you need to have 3 bonds involved in this in order to express the chirality. So if you think about this in a slightly different way, you might say, well, let's have this unit and let's expand in multipoles and so on, and you turn to Jackson and the relevant things, and as you know, you get dipoles and quadrupoles and octopoles and so on. We've sort of done all that sort of stuff. And who knows, does anybody know what happens after an octopole? No, you're wrong. It's a barber's pole. You can find it further on in the 4th edition of Jackson. Anyway, so this is, you find these on the street at Mass Avenue. Anyway, so you can do the same sort of thing there as I just expressed. The actual version of this, the actual way it works out in electrodynamics is a little bit different. It's sort of, it's sort of semi-conductive if you like, but ultimately it's all quantum mechanical. But the point is the same sort of chiral preference can be expressed in this way. And so something like proto-RNA, which is, sort of helical, is different from the opposite one. Okay, that's the point, and that's the preference, and it's a reflection of the cosmic rays that are irradiating it. And there's another effect, actually, it's the first one we discovered, and after we did, and there's actually a second effect, is that if these chiral units have a magnetic dipole locally, not globally, but just a permanent magnetic dipole, and it has a preference with respect to the electric dipole, that also is a chiral term, and that was actually the first one we discovered. We were sort of quite pleased with this, and then somebody pointed it out that Zeldovich had discovered the same thing in the 1970s in a paper that, as far as I can tell, no one has ever cited. But and he did it in a very different way with a collaborator. He did it in a very different way, quantum mechanically. But it's exactly the same set of results. So there is some sort of preference. It's a very small chiral preference. It's never going to be large. It involves inevitably the product of the fine structure constants, and it might be as small as 10 to the minus 10. It could be as high as 10 to the minus 6. It depends on the fount you use and things we don't fully understand yet. But it's a very small number. But the previous efforts along this line by Salamonon were 10 to the minus 17. So this is an improvement. And our contention is that if you then couple this with some population dynamics, and remember you've got many replications, you keep going around these cycles and so on, struggling to reproduce and find mutations that are going to allow you to survive. And there's an almost anthropic preference coming in here, and these are the sort of examples of the sort of equations you can play around with in the most simplest form. And basically this sort of Manichaean struggle between live and evil, almost equal to start off with, is one, obviously, by definition, by the live, in fact, you accelerate this by having a conflict between live and evil. It's not just allowing them passively to evolve. You want them to fight. They fight for resources, and they poison each other. I mean, this is basically what happens. And so that's sort of, expressed here, and very primitive life forms replicate extremely fastly, as people in emergency rooms know. And so you... this sort of evolution generally, with mutation and replication and so on, can actually lead a very small chiral bias, as long as it's a very permanent one that can't change. It will then lead to preference and so on. So that's the basic idea. Where this sort of ends up, I think, and we're sort of very keen on this. There's relatively cheap and easy and quick experiments that can be done along these lines, using E-beams and all of that. And also, of course, there's sample returns happening, and we know a little bit about this in recent years, and there's more stuff on the way. And so, I won't say what we're going to see from either of these. I'm not making any great predictions, but I do predict that we'll learn a lot from them. So thank you very much indeed.
That will land on Mars and start digging, hopefully by March 2021. If they find a different chirality, would that disprove your model in the sense that Mars was exposed to the same cosmic rays?
Well, you say it's the same cosmic rays. The cosmic rays are not the problem. I think it's really what I call the fount. It's the environment. There's a lot of difference in terms of the irradiating particles between having something 100 meters underground and having something, on the surface of the Earth. There's a difference at earlier times. I do not know how robust the chiral preference is as a result, of this, because it depends on details of the biological molecules. I don't know whether it's robust, but it looks to us that it is basically robust. But I can't really give a good answer to that question and say this is as far as we've got.
But if they find the same chirality, it will be consistent with your idea.
Not necessarily. Not necessarily. I mean, I think if you go to lots of different sites and it's 50-50, then that would almost certainly persuade you that it was a pure fluke. It's an unstable equilibrium, and you break the symmetry either by a spontaneous fluctuation, breaks the symmetry one way or the other. But for larger reasons, we argue against that in general. Owen.
I was just wondering. I vaguely remember that in meteorites they've discovered amino acids.
Yes.
And that they did not express chirality, that they were roughly 50%
Well,
left and 50%?
No, there are some examples of that. But we're more interested, less in the amino acids themselves, the prebiotic molecules. We're interested in what happens after that. You know, when there's a place where we don't have any samples, but
because of amplification.
Yes, yeah. I mean, there's a whole, there's armies of people who work on this, and in the journals and so on, and this is very important. But I think, maybe we're hubris here or whatever, but it looks most likely that is the sort of soft spot. Is when you're just starting to make something that's replicated.
Any urgent last question?
How much initial asymmetry fluctuation is enough to produce, after all this amplification, the total rule of one chirality as we see now on Earth? So you say it all started from some initial random fluctuation in chirality that was amplified.
No, not a random fluctuation. It really depends on the cosmic rays having this property.
Yeah, but initially, if it was exactly the same of the evil and live, then they will also
there's symmetry. But it's the whole point is it's causal. I mean, if you to use something that's a little dangerous under these circumstances, an alternative title for this, rather than the jokey one I gave, is the doctrine of original spin. And I sort of used that yesterday. That's of course the spin of the neutron. So we'll be careful about that. But that's what drives it. And then causally, there's a preference for one of the chiralities over the other. It's not a fluctuation.
Okay, we got to our time limit. Let's thank Roger.